Welcome back to the Deep Dive. We're jumping straight in today with, well, a pretty provocative statement.
Oh, yeah. Which one?
It came from Elon Musk, actually. Shook things up a bit in tech and crypto circles.
I think I know where you're going with this.
He stated quite clearly that AI cannot crack Bitcoin.
Right. And he added that AI cannot defy fundamental math.
Exactly. Which, is a fascinating thing to say right now.
Definitely. Especially with AI seemingly advancing exponentially and all the buzz around quantum computing, too.
It really makes you wonder, if you're involved in digital assets or just interested in future security, is he right? Is Bitcoin genuinely protected by some kind of immovable math barrier, at least against conventional AI?
Well, that's pretty much our mission for this deep dive, isn't it? We've looked into the technical side, the sources explaining the cryptography.
Trying to understand the real limits AI faces here.
Oh.
We want to give you that clarity. What are the actual barriers protecting Bitcoin, and what can AI realistically do or not do in crypts analysis?
Okay, so to really get it, I think we need to break it down, maybe into 3 key areas.
Sounds good. What have you got?
First, we absolutely have to understand the cryptographic foundations. What is the math fortress protecting Bitcoin?
Right, the pillars.
Second, why do AI's strengths, things like pattern finding and optimizing, seem to fail against these specific mathematical problems?
And third,
we need to tackle that common confusion point. The difference between the AI we have now and the actual potential long-term disruptor, which is quantum computing. They're not the same threat at all.
Okay, perfect. Let's start with that fortress then, the core defense.
Yeah.
Sources are clear. It's not just one thing, right? It's a layered system.
Exactly. Multiple, robust, well-tested mathematical mechanisms working together.
So layer 1, the absolute first line of defense.
That's got to be SHA-256, secure hash algorithm, 256-bit.
Okay. And this isn't some brand new experimental tech.
Not at all. It's been around for ages, relatively speaking. Part of the SHA-2 set the NSA designed, published by NIST way back in the early 2000s, so it's faced, tons of scrutiny.
And its core function is, it takes any data, big or small.
Any input at all, yep. A word, an entire book, transaction data, and it crunches it down into a fixed-length outcome.
That 64-character hexadecimal string we sometimes see.
That's the one!
Yeah.
But the real magic isn't just the fixed length. It's the unidirectionality.
Meaning it only goes one way.
Precisely. Think of it like, a super secure blender. It's easy, computationally speaking, to throw ingredients in and get the smoothie out, calculate the hash from the input.
Okay.
But try figuring out the exact original ingredients just by looking at the smoothie. Forget it. With current math and computing power, it's practically impossible to reverse SHA-256. You can't find the input just from the hash output.
Got it. So SHA-256 is like the vault door itself. Super strong, can't go backwards through it. What about making sure everyone agrees on the state of the vault, the consensus part?
That brings us to proof of work. Probably it.
Right. This is where the mining comes in.
Exactly. It's the mechanism that ties everything together using that hashing power. Miners are essentially running data through that SHA-256 blender over and over.
Trying different recipes.
Kind of. They're looking for a very specific output by adding a random number, a nonce, until the resulting hash meets a certain difficulty target set by the network.
And because that takes so much effort, so much energy,
it secures the network, it makes it decentralized and incredibly expensive and difficult for any single entity to cheat or take over.
Okay, so we have the hash function, the consensus mechanism. What about securing individual transactions? Making sure my coins are mine?
That's where the third pillar comes in, elliptic curve cryptography. Specifically, ECDSA, the elliptic curve digital signature algorithm.
Sounds complex.
The math is, but the concept is about digital identity. Bitcoin uses a specific curve, SECP256K1. This is what lets you create a digital signature with your private key, proving you own the coins you're trying to send without revealing the key itself.
Authentication and proof of ownership.
Exactly. So you've got the hash blender, the energy-intensive consensus, and the unique digital signature. That's the trifecta.
A pretty formidable defense. Which brings us back then to Musk's point. AI, even with its incredible progress, why can't it just muscle through this math? It's great at patterns, complex problems.
This is where it gets really fascinating, actually, because cryptography, almost by definition, exposes the limits of current AI.
How so?
AI thrives on patterns, learning, recognizing, predicting based on vast amounts of data, spotting faces, translating languages, predicting market trends. Those are computationally tough, sure, but they involve finding underlying structures.
But crypto problems are different.
Fundamentally, problems like reversing a hash function or factoring huge numbers, they belong to a class of problems, think NP complexity, where AI's pattern matching skills just don't offer much of an advantage.
Because there are no patterns to find.
Pretty much. Good cryptography is designed to produce output that looks completely random, statistically speaking. No shortcuts, no structures for an AI to learn and exploit. It's like trying to predict the next roll of a perfectly fair die based on past rolls. It just doesn't work.
Could you elaborate a bit on that NP complexity idea? How is it different from the pattern problems AI is good at?
Sure. Think about verifying a solution versus finding it. With many complex problems AI tackles, like finding the best route for a delivery truck, verifying if a proposed route is good is relatively easy, but finding the absolute best route among billions of possibilities is hard. AI uses heuristics, learned shortcuts.
Okay.
But with something like trying to find the input for a given SHA-256 hash, verifying a potential input is super fast. Just hash it and see if it matches. But
Wonderful.
finding that input, there are generally no known shortcuts better than brute force, basically, trying every single possibility.
Which is computationally astronomical.
Exactly. The search space is just unimaginably vast. AI doesn't magically shrink that space for these kinds of problems.
Which loops back to that crucial distinction Musk made. Optimization versus rupture.
Yes, that's spot on. Musk said AI can improve the efficiency of hashing, but not crack it. Big difference.
Explain that difference. Optimization is like.
Optimization is like tuning a car engine. AI could maybe help miners use energy more efficiently or manage their hardware better. It's working within the existing rules, making the process faster or cheaper.
But rupture.
Rupture is trying to break the rules entirely. Defy the mathematical gravity, so to speak. It means doing the impossible according to current understanding, like reversing the hash function, finding a pre-image, or finding two different inputs that somehow produce the same hash, a collision.
And the numbers involved in trying to force that rupture on SHA-256 are, well, mind-boggling.
They really are. Forget astronomical, they're cosmological. To find a pre-image for SHA-256, you'd need something in the ballpark of 2 to the power of 255 operations. More operations than estimates of atoms in the observable universe. It's just not feasible with classical computers. Finding a collision is slightly easier, theoretically, but still requires around 2 to the power of 128 operations, still way, way beyond reach.
So for any computer working classically, including all current AI running on standard hardware, it's effectively impossible. The math barrier holds.
That's the consensus, yes. Musk's statement aligns with the cryptographic understanding here. You can't just throw more current computers or current AI algorithms at it and expect a breakthrough. You need a different kind of computation.
Okay, that's a perfect transition, because this is where a lot of the confusion comes in, right? People hear AI threat and quantum threat and sometimes conflate them.
Absolutely. We need to draw a very clear line here.
Conventional AI, the stuff we have now.
It's built on classical computers. Silicon chips, bits being zeros or ones. It follows deterministic rules, even if it seems intelligent.
And quantum computing.
That's a whole different paradigm. It uses quantum mechanics principles like superposition, where a qubit can be 0 and 1 simultaneously, and entanglement. This potentially allows quantum computers to perform certain calculations exponentially faster than any classical computer ever could.
And there's one specific quantum algorithm that always comes up in these discussions.
Shor's algorithm. Yep, that's the boogeyman for much of current public key cryptography.
Why is it so dangerous?
Because Shor's algorithm, if run on a large enough, stable enough quantum computer, could efficiently factor large prime numbers.
And that matters because?
Because the security of many systems, including the ECDSA digital signatures Bitcoin uses, relies on the mathematical difficulty of factoring those large numbers. You can factor them easily. You can potentially derive someone's private key from their public key, breaking the signature scheme.
Okay, so quantum could theoretically break the signature part of Bitcoin. What about the hashing part, SHA-256? Is it vulnerable too?
That's actually a bit of good news, relatively speaking. Hash functions like SHA-256 are generally considered much more resistant to quantum attacks than public key systems based on factoring or discrete logarithms.
How so?
Quantum computers might speed up the process of finding collisions or pre-images using algorithms like Grover's algorithm, but it's not the same exponential speedup Shor's provides against factoring. It might effectively halve the bit strength, making SHA-256 act more like SHA-128 against a quantum attacker, but SHA-128 is still considered pretty strong.
So the hashing might hold up better, but the signatures are the weak point for quantum.
That's the current thinking, yes. The community would likely need to transition to quantum-resistant signature algorithms first, while SHA-256 might survive longer, perhaps needing a move to SHA-384 or SHA-512 eventually.
But let's stress the timeline here. This isn't happening next week, is...
Oh, definitely not. Building fault-tolerant quantum computers capable of running Shor's algorithm against realistic cryptographic key sizes is an enormous engineering challenge.
We're talking.
The consensus is still likely decades away. It's a real theoretical threat. And the groundwork for post-quantum crypto needs to happen now, but it's not an imminent danger that invalidates Bitcoin today. People shouldn't confuse the limitations of current AI with this future quantum potential.
Right. So wrapping this part up. Conventional AI is bound by classical computation limits, which SHA-256 currently laughs at. Quantum computing is a future threat, especially to signatures, but it's still a good way off.
Exactly.
Which leads to the practical question. If the core math is actually solid against today's AI, and quantum is still on the horizon, where are the real risks to Bitcoin and people's crypto assets right now?
Well, the risks are definitely real, but they almost always come back to us, humans, and how we implement and interact with the system.
Not the fundamental math itself.
Rarely, if ever, the fundamental math. The vulnerabilities lie in the layers built around that math. Our sources usually group them into, say, 3 main categories.
Okay, what's the first one?
Human factors. This is the big one. Losing your private keys. Writing down your seed phrase where someone can find it. Clicking on phishing links. Getting tricked by social engineering. If you give away your key, the world's best cryptography can't help you.
So, user error and security practices.
Absolutely. That's probably where most losses occur.
What's the second category?
Software implementation. Bugs or vulnerabilities in the actual code.
You mean in Bitcoin Core itself?
Potentially, though that's heavily scrutinized. More often, it's in third-party wallets, exchanges, smart contracts layered on top, or other bits of the ecosystem. A tiny coding mistake could open up an unexpected vulnerability, even if the underlying crypto math is sound.
Like a weak link in the chain.
Precisely. A side channel attack, maybe, that bypasses the main crypto?
And the third area of real risk.
Network-level attacks. The most famous is the 51% attack.
Where someone controls the majority of the mining power.
Yeah. If you control over half the network's hash rate, you could potentially double-spend coins or prevent legitimate transactions from confirming.
Is that a realistic threat?
It's theoretically possible, but practically very difficult and incredibly expensive for a large network like Bitcoin. You'd need immense resources, and the economic incentives often don't line up. But it's not mathematically impossible, unlike cracking SHA-256 with current AI.
So the takeaway is,
Yeah.
the real dangers are in how we use the system, how we build on it, and potentially how the network itself is governed by hash power, not in AI breaking the core math.
That sums it up nicely, yeah. The academic and security consensus really supports Musk's point on the math being resistant to current AI. The weak points are almost always human or implementation-based.
Okay, this has been a really important clarification, I think. That Musk, quote, generated a lot of heat, maybe not enough light. Let's try and synthesize the key takeaways for everyone listening.
Sounds good. First off, Musk's claim that conventional AI can't just crack Bitcoin seems technically sound. It reflects the known limitations of classical computing, which is what current AI runs on, against these specific hard mathematical problems like SHA-256.
Right. The math barrier is real for today's tech.
Second, that distinction we hammered on, optimization versus rupture. It's crucial. AI might help make mining more efficient, but that's working within the system. It's not breaking the system's cryptographic foundations. That requires overcoming those insane 2255 type numbers.
Improving speed is not the same as defying mathematical gravity. Got it.
And third, looking ahead, the real cryptographic challenge isn't current AI. It's preparing for the eventual transition to post-quantum cryptography. That's where the cryptographic community needs to focus resources and planning, likely for new signature schemes first.
Focus on the long-term quantum threat, not the misplaced fear about today's AI breaking the fundamentals.
Exactly.
So thinking about the listener, what does this mean for you and securing your own digital assets? It seems the overwhelming message is that the biggest threats aren't super intelligent AIs cracking algorithms.
No, the biggest threats are much more mundane, unfortunately.
Losing your keys. using a dodgy exchange,
Yeah.
falling for a scam. Which leads to a final thought, maybe a bit provocative.
Go for it.
In a future where AI does optimize almost everything else, driving our cars, managing logistics, maybe even aspects of our health, will the hardest part of securing digital wealth still come down to us? To plain old human vigilance, careful key management, and avoiding simple mistakes? Is that the final frontier AI can't automate away for us?
That's actually a really interesting question to ponder. Will human fallibility remain the weakest link even as everything else gets smarter? Something to definitely chew on.
Indeed. Food for thought as you continue your own research.
Hope this deep dive was helpful.
Thanks for joining us on The Deep Dive. We'll catch you next time.